Section 33.2 Velocity distribution in one dimension. Let's first look at the speed distribution of the gas particles in one dimension, the x dimension. Boltzmann found that the probability of finding a gas particle moving at a speed between Vx and Vx plus dVx is proportional to this exponential function, e to the power of negative mvx squared over 2 kBt. In general, Boltzmann found the probability of finding a particle with energy epsilon is proportional to e to the power of negative epsilon over kBt. So right here, epsilon is 1/2 mv squared. And then we know this probability is proportional to this exponential function. And also, we have a range. The range is from Vx to Vx plus dVx. Therefore, we have to multiply this exponential function with the range of the speed, dVx. And then we can write it in the form of these two equations. The probability of finding a particle moving in the x direction at a speed between Vx and Vx plus dVx is equal to the probability density times dVx. So again, this is probability density. It's probability divided by the range of the speed. And over here, this f is equal to a constant, times this exponential function, e to the power of negative kinetic energy over kBt. So again, this f of Vx is the probability density of finding the particle traveling at a speed between Vx and Vx plus dVx. We can calculate this a. The reason is we know the total probability of finding a particle with a speed Vx between 0 and infinity is 100%. So the speed has to be between 0 and infinity. Therefore, this integral from 0 to infinity of f Vx dVx, so this is probability density. And this is the probability of finding the particle moving at a speed between Vx and Vx plus dVx. And then if we integrate this from 0 to infinity, it has to be 100%. So that's why we have this equation. Again, over here, this is the probability of finding the particle moving at a speed between 0 and infinity in the x direction. It has to be 100%. Now, how do we solve this? We'll do a variable substitution first. So first, this part looks very complicated. So we set q, a new variable, is equal to Vx times the square root of m over 2 kBt. So this part, this whole thing, becomes negative q squared. So this part is q squared, and then there's a negative sign. All right? So this is to simplify this Gaussian function to e to the power of negative q squared. And by setting q to be Vx times the square root of m over 2 kBt, we know V sub x has to be q times the square root of 2 kBt over m. So we can plug this in here. And then we have this integral. All right. Fortunately, this part, this square root, is a constant. So we take this out of the integral. A, the normalization factor, is also a constant. How do we integrate this? Well, the value of this is simply square root of pi over 2. And then we can determine the value of a. A is the square root of 2m over pi kBt, or the square root of 2 uppercase m over pi RT. So this m is the mass of a gas particle. And this m is the molar mass of these gas particles. Kb is the Boltzmann constant. R is the ideal gas constant. So the molar mass m is the mass of a gas particle multiplied by the Avogadro constant. And this R is also Kb times the Avogadro constant. So basically I multiplied the top and the bottom by the same factor, the Avogadro constant. So again, m is the mass of one gas particle. This uppercase m is the molar mass. This m usually is in kilogram when you need to use this equation. And this uppercase m is kilogram per mole when you use this equation. The reason is we like to stick with the SI units. So again, this is the relationship between this uppercase and lowercase m. This is the relationship between the gas constant and the Boltzmann constant. So we have two equations for the probability density of speed. So one here, one here. They are exactly the same. It's just this m over kb is replaced with uppercase m over r. Same here. You have this lowercase m over kb. It's the same as this uppercase m over r. Again, the uppercase m is the molar mass, typically in kilogram per mole. Now let's look at the distribution of velocity. That's very simple. It's just 1/2 or 50% of the probability density of speed. This is because for each speed, Vx, there are two possible velocities. It can be Vx positive and Vx negative. The particle may move towards the positive direction or the negative direction. And these two velocities have the same probability. So we got two equations here. So this one, Vx positive and Vx negative, they belong to the same speed. And also, due to the symmetry, we know this f of positive Vx is equal to this f of negative Vx. And therefore, we know this probability density of positive Vx or the probability density of the negative Vx are both equal to 1/2 of the probability of this speed, V sub x. So that's very simple. We get the normalized Maxwell-Boltzmann velocity distribution. It's just 1/2 of this or 1/2 of this. So again, the square root of 2 over 2 is simply the square root of 1/2. So we flip this 2 to the bottom, right? Again, if you need to do numerical calculations, I recommend you to use the SI units, and therefore keep this kilogram per mole as the unit of this uppercase m, or kilogram as the unit of this lowercase m. For example, if you're looking at hydrogen, then the mass of hydrogen is this. The molar mass of hydrogen is this, 0.002 kilogram per mole. That's the molar mass of the hydrogen molecule in SI unit. So again, I know the molar mass of hydrogen is 2.016 atomic mass unit. However, that's not the SI unit. The SI unit over here, you can see it's kilogram per mole. It's not gram per mole. So let's look at one more example. Let's look at the one-dimensional velocity of CO2 at the room temperature. By looking at the probability density function, we can tell this part is maximized when the speed is 0. Well, when the speed is 0, the velocity is also 0, right? So we can calculate this probability density. We plug in the numbers. When v sub x is 0, this exponential function is simply 1. We just need to look at this square root. The square root of molar mass over 2 pi RT. This is the molar mass of CO2. Down there we have 2 pi RT. The result is 0.0017. And this is the unit of speed. And we're taking the reciprocal of it. Why? Because this F is probability density. That's probability divided by the range of velocity. So on top, you have no unit. On the bottom, the range of velocity has a unit, m/second. So remember this number, 0.0017, and then look at this graph. This is CO2 at 298 K. So at a 0 speed, this probability density is maximized at 0.0017, right? Okay, so now let's do another calculation. What if the speed is 200 meters per second, and then you have two possible velocities? It can be 200 or negative 200 if CO2 is moving towards the positive or negative direction. So first, let's look at the graph. 200, maybe right here. It's 1/5 of this range. So right here. Move up. It's probably 0.001. Okay, so that's the probability density when the velocity is negative 200. What about positive 200? Well, this picture is symmetrical, so it's also about 0.001. Let's do the calculation. Again, we plug in the numbers. So we learned this part is simply 0.0017, the maximum value of this function, this probability density function. We now have to look at the exponential function as well. We plug in this Vx is equal to 200. We evaluate this, we get 0.0012. The unit is the reciprocal of meter per second. All right. So again, when this velocity is negative 200 or positive 200, the probability density is roughly 0.0012. So somewhere here. So feel free to plug in some other numbers like 1000. You'll see the probability density is really, really small from the graph and by doing the calculation. So imagine you plug in 1000 instead of 200 here. The final result is going to be really small. Now let's evaluate the average velocity of the gas particles in the x direction. Without doing any calculation, you should realize that it's 0. Because if you have a lot of gas particles, some are moving in the positive direction, some in the negative direction. And the probability density of moving at positive Vx is equal to that of negative Vx. They cancel. So overall, you'll have a 0 average velocity. But still, let's do the math. So this is the average velocity. How do we get the average velocity? Well, this is the velocity, and this is the probability of having that velocity. And then we integrate this from negative infinity to positive infinity. Pay attention to the sign here. And the sign here. This is because we're talking about velocity. Therefore, we have negative signs and positive signs. So how do we integrate this? We plug in this f function here in this integral. This is the f function. This is the probability density. And then multiply by dvx. That will give you the probability of finding the particle moving at a velocity between Vx and Vx plus dVx. All right, so this part gives you the probability of finding the particle moving at a velocity of Vx with an arrow. Okay, and Vx plus dVx also with an arrow. All right, so this is probability weighted Vx, and then we integrate from negative infinity to positive infinity. Now we have to look at this Vx and this dVx. We can put them together because this is equal to the differential of half Vx squared. That's very simple. This is just single variable a differential calculus. And remember, when we are talking about the motion in one dimension, the velocity squared is equal to the speed squared, because the velocity is simply either plus or minus speed. So we have this equation. And then we set q to be mvx squared over 2kbt. So this whole thing is just our q. All right? And then we can just express this half Vx squared. Right? So you have Vx squared over 2 here. It's just q times kbt over m. By doing this variable substitution, we simplify this integral. And this average velocity is the integral of, we copy this constant here, and this becomes e to the power of negative q. All right? And over here, this Vx times dVx is the differential of half Vx squared. And half Vx squared is this guy. So I plug in this guy here. Now let's pay attention to the lower limit and upper limit. So the velocity is from negative infinity to positive infinity. All right? In this case, this q, what's the range of this q? The range of this q is now from positive infinity to positive infinity, because over here this Vx is squared. All right, this Vx is squared. And then you just need to integrate this. Well, however you want to do this. I mean, if you have the same lower limit and upper limit, the result is going to be 0. All right? So actually, if you realize that, again, the gas particles are moving in the positive direction and negative direction. So on average, half towards the right direction, half towards the left direction. And the probability of finding the particle moving at, for example, 200 meters per second versus negative 200 meters per second are exactly the same. So they cancel. Again, this particle moving at negative 200, this particle moving at positive, they cancel. So again, whatever velocity you find on the positive side, you will also find the same probability density on the negative side. So that's why they cancel. Well, now let's calculate the root mean squared velocity. So this is more complicated. We'll have to look at the average of the velocity squared first. So this is the average of the velocity squared. And the velocity squared is equal to the speed squared. Again, we're talking about just one dimension. All right? So plus minus 200 squared is equal to just 200 squared. And in this case, we'll just do the weighted average of Vx squared. We plug in this probability density function here. All right, so this is the probability density times dVx. That gives us the probability. All right, and then we need to know the average value of Vx squared. So how do we integrate this? Again, variable substitution. We have to set this q now this time to be just Vx times the square root of m over 2 kBt. Why do we do this? By doing this, we simplify this Gaussian function. This Gaussian function becomes e to the power of negative q squared. That's it. So this becomes e to the power of negative q squared. And now we can also write Vx is equal to q times the square root of 2 kBt over m. So it's just the reciprocal of this guy. We plug in the expression of q in Vx. We have this equation for the average value of Vx squared. Again, the exponential function becomes e to the power of negative q squared. And this is actually here, Vx. All right? And then we clean up. We look at all those constants, put them together. So this is the constant part being combined. And then we have this integral. The integral of q squared times e to the power of negative q squared. Q is from negative infinity to positive infinity. Well, this integral is simply the square root of pi over 2. You can compute this using Wolfram alpha. Well, you can also convert this to polar coordinates. And then we can derive this integral analytically. And you will get this result. So we plug in this value to here. Square root of pi and the square root of 1 over pi cancel. And then this 2 and this 2 cancel. So in the end, we have a very simple expression for the average Vx squared. It's just kBt over m. And again, the velocity squared is equal to the speed squared in one dimension. So we have, again, the average value of the velocity squared is equal to the average value of the speed squared in just one dimension. It's just kBt over m. And not just in the x direction. We can have the same equation for y direction and z direction. Therefore, the average three-dimensional translational energy is simply the sum of this guy and this guy and this guy. The result is 3/2 kBt. So if you have a bunch of gas particles moving around at temperature T, we can predict the average kinetic energy of these particles is 3/2 kBt. That's it. So we have this equation by taking the square root of both sides. And then we get the root mean squared speed of the gas particles. It's very simple. It's the square root of 3 kBt over m. Just a reminder, if you find it inconvenient to calculate the mass of a gas particle, well, very simple. You can replace that with the molar mass in kilogram per mole. At the same time, replace the Boltzmann constant with the ideal gas constant R. So again, this notation is the average of V squared.